Close your eyes. Now ask yourself a question that sounds simple, but isn't. Does the room around you still exist?
Not do you believe it exists. Not is there evidence it exists. Does it actually, physically, definitively exist right now while your eyes are closed and no part of your sensory system is measuring it? Your instinct says yes. Of course it does. You have been in this room. You will open your eyes and it will be there. The chair, the wall, the window, they are real objects in a real space, and your looking at them has nothing to do with whether they exist. That instinct is almost certainly wrong.
Not as a metaphor, not as a philosophical game, as a hard, experimentally confirmed, mathematically precise conclusion of the most successful scientific theory ever constructed. Quantum mechanics, the theory that describes every atom, every electron, every photon of light, tells us something that contradicts our every intuition about the nature of things.
At the fundamental level of reality, objects do not have definite properties until those properties are measured. Before observation, a particle does not have a definite position. It does not have a definite speed. It does not have a definite spin. It exists as a superposition, a simultaneous occupation of multiple possible states. And the act of measurement is not the revelation of a pre-existing fact. It is the creation of one. The universe, at its most fundamental level, does not commit to a definite reality until something forces it to. This alone is disturbing enough. Scientists have spent 100 years trying to find a way around it, a hidden mechanism that restores our common-sense picture of the world, a deeper layer of reality where things are definite and real, whether or not anyone is looking. They failed.
But in failing, they found something even stranger than the original problem. They found that two particles, separated by any distance, by the width of a laboratory or the width of a galaxy, can be so deeply connected that measuring one of them instantly determines the state of the other.
Not after a signal has traveled between them, not because of any force or field connecting them. Instantly, completely, regardless of distance. Einstein called this spooky action at a distance. He spent decades trying to prove it was impossible. He was wrong. Spooky action at a distance is real. It has been measured. It has been confirmed in dozens of experiments with increasing precision. It is one of the most solid experimental facts in modern physics. And what it implies about the nature of space, about the nature of information, about the nature of reality itself, we have not yet fully absorbed.
This is the story of quantum entanglement, of the scientists who discovered it, the scientists who refused to believe it, and the experiments that settled the question in the most unsettling way possible. It is a story about what the universe is made of at the deepest level, and it begins, as so many of the deepest stories in physics begin, with a conflict between two extraordinary minds. To understand why entanglement was so disturbing, we need to understand what quantum mechanics was claiming, and why a man of Einstein's intellectual caliber spent 20 years trying to prove it wrong. By 1927, a revolution had occurred in physics. A group of young scientists, Heisenberg, Bohr, Born, Dirac, Pauli, had assembled the mathematical framework of quantum mechanics. It was built from years of experimental anomalies, the photoelectric effect, atomic spectra, the double-slit experiment. The framework was strange, deeply counterintuitive, and unlike anything physics had produced before. But it worked. The predictions were extraordinarily precise. Every experiment confirmed it.
The theory matched reality with an accuracy that no previous physical theory had approached. And yet, what the theory said about reality was deeply unsatisfying. Quantum mechanics said that a particle, an electron, a photon, does not have a definite position before it is measured. Before measurement, the particle is described by a wave function, a mathematical object that encodes not where the particle is, but the probability of finding it in various locations if you look.
The wave function is not a description of our ignorance. It is not saying the electron is somewhere definite and we just don't know where. It is saying the electron genuinely has no definite position. It is, in a precise mathematical sense, everywhere it might be, simultaneously, until the moment of observation.
This is superposition, and it is not a metaphor. When you measure the electron, when a detector clicks, when a screen lights up, the wave function collapses. The electron appears at one specific location. The multiple possibilities resolve into one actuality.
Where was the electron before the measurement? The theory's answer is nowhere specific, in superposition, in multiple possible places at once. Reality, at its most fundamental level, is not a collection of objects with definite properties existing independently of observation. It is a collection of possibilities that become definite only through the act of measurement.
Albert Einstein found this unacceptable. Einstein was not opposed to quantum mechanics because he failed to understand it. He understood it better than almost anyone. He had, in fact, helped create it. His explanation of the photoelectric effect in 1905 was one of the first quantum results. What Einstein rejected was the interpretation.
He was a realist in the philosophical sense. He believed that the physical world has a definite state, that particles have real positions, real velocities, real properties, whether or not anyone is measuring them. The moon, he famously asked a colleague, does not cease to exist when no one is looking at it. He believed quantum mechanics was incomplete, that beneath the probabilistic wave function, there was a deeper layer of reality, what he called hidden variables, that determined outcomes in advance. The randomness of quantum mechanics was, on this view, like the randomness of a coin flip, not truly fundamental, but the result of our ignorance of underlying details that were, in fact, deterministic. And he had a second belief, equally deep. He believed in locality, the principle that what happens at one location cannot instantly affect what happens at another, distant location. Causes propagate through space at finite speeds. Nothing travels faster than light. These two beliefs, realism and locality, formed what philosophers call local realism. And it was the foundation of Einstein's intuition about the physical world. Quantum mechanics, he was convinced, must be incomplete because its implications threatened local realism. In 1927, at the famous Solvay conference in Brussels, Einstein and Bohr met face-to-face for a formal debate. It was one of the most extraordinary intellectual confrontations in the history of science. Every morning during the conference, Einstein arrived at breakfast with a new thought experiment, a precisely constructed hypothetical designed to show that quantum mechanics was internally contradictory, that there was a way to extract more information about a particle than the uncertainty principle allowed. Every evening, Bohr would retire to his room. He would pace, he would argue with himself, he would work through the mathematics. And the next morning, he would return with a careful, quiet, devastating response, pointing to exactly where Einstein's reasoning had gone wrong. This happened every day for the duration of the conference. By the end, Einstein had publicly acknowledged that Bohr had answered every challenge. He did not change his mind. 3 years later, at the 1930 Solvay Conference, Einstein arrived with what he believed was his most powerful attack: the lightbox experiment, a thought experiment designed to simultaneously measure both the energy and the timing of a photon with perfect precision, violating Heisenberg's uncertainty principle. Bohr was reportedly shaken. He spent a sleepless night working through the argument, and in the morning, he returned with an answer that used Einstein's own general theory of relativity, the equations relating mass, energy, gravity, and time, to show that the uncertainty principle was preserved, that the very act of measuring the box's weight changed the rate of the clock inside it by exactly the right amount. Einstein had tried to defeat quantum mechanics using his own greatest theory, and Bohr had used that same theory to save quantum mechanics. In 1935, Einstein, working with two colleagues, Boris Podolsky and Nathan Rosen, published a paper of just 6 pages. The paper is known by the initials of its authors, EPR. The argument goes like this. Imagine two particles that have interacted and then moved apart, traveling in opposite directions. Quantum mechanics describes their combined state as a single wave function, a mathematical object that applies to both particles together. Now measure a property of one particle, say its position. The instant you make this measurement, quantum mechanics predicts that the wave function of the second particle collapses too, even if the second particle is on the other side of the laboratory, even if it is on the other side of the planet, even if it is light years away. EPR said, "This is impossible." If the two particles are far enough apart, no signal can have traveled between them in the time between the measurements. Einstein's own special relativity forbids it. Information cannot travel faster than light. And yet, quantum mechanics requires an instant connection. Therefore, EPR concluded, quantum mechanics must be incomplete. The second particle must have had a definite position all along, determined before any measurement, and the quantum mechanical wave function simply failed to capture this fact. There must be hidden variables. Einstein called the alternative spooky action at a distance, and he regarded it as proof that quantum mechanics was incomplete. Bohr published a response. Many physicists felt it was not an answer, it was a refusal to answer. And for 20 years, the question remained unresolved. Einstein's hidden variables and Bohr's quantum mechanics made exactly the same predictions. The debate was philosophical, not scientific. And then, in 1964, a physicist named John Bell changed everything. John Bell was an Irish physicist working at CERN, the particle physics laboratory in Geneva. He was deeply unsatisfied with the state of the foundations of quantum mechanics. The Bohr-Einstein debate had ended not in a resolution, but in a kind of uneasy truce. Bell asked the foundational question again. He asked, is there a mathematical difference between a world with hidden variables, a world where particles have definite properties before measurement, and a world described by quantum mechanics, where they do not? The prevailing assumption was no. That was why the debate had seemed unresolvable. But Bell suspected the assumption was wrong. He worked through the mathematics of local hidden variable theories, theories in which particles have definite pre-existing properties, and measurements simply reveal those properties, with no spooky action required. And he derived a result that surprised everyone. Bell's theorem, published in 1964, showed that any local hidden variable theory must make predictions that satisfy a specific mathematical inequality, now called Bell's inequality. The correlations between measurements on two distant particles in any locally realistic theory cannot exceed a certain limit.
Quantum mechanics predicts that the correlations between entangled particles violate this inequality. The predicted correlations are stronger than any locally realistic theory can produce. This was not a philosophical claim. This was a mathematical result. Bell had found a measurable difference between a world with hidden variables and a world governed by quantum mechanics.
If you could measure the correlations between two entangled particles with sufficient precision, you could test Bell's inequality. If the inequality was satisfied, Einstein was right. If the inequality was violated, Einstein was wrong.
The most famous and decisive experiment was performed in 1982 by Alain Aspect and his team at the Institut d'Optique in Paris. Aspect's experiment used pairs of photons, particles of light, created through a process in which a single high-energy photon is split into two lower-energy photons with correlated polarizations. These two photons, once created, are quantum mechanically entangled. The two photons were sent in opposite directions to detectors separated by more than 10 meters. At each detector, the polarization of the photon was measured, but the direction of measurement was chosen randomly after the photons had already left the source, so that no signal traveling at or below the speed of light could have carried information from one measurement to the other.
Aspect's team measured the correlations between the two detectors thousands of times. The result was unambiguous. Bell's inequality was violated by a statistically decisive margin. The correlations between the entangled photons were stronger than any locally realistic theory could produce. The universe is non-local.
Alain Aspect won the Nobel Prize in Physics in 2022 for this work, along with John Clauser and Anton Zeilinger. The Nobel Committee was explicit. The experiments showed that the world cannot be explained by any theory that assumes both locality and realism. Einstein was wrong.
Not about relativity, not about the speed of light, not about gravity, but about local realism, about the intuitive picture of a universe in which objects have definite properties and distant events cannot instantly influence each other. That picture is incompatible with the way the universe actually behaves.
Now, a careful clarification. Quantum non-locality does not mean that information or signals travel faster than light. You cannot use entanglement to send a message instantaneously. When you measure one entangled particle, the result you get is random, and the person measuring the other particle, far away, also gets a random result. It is only when you compare the two results, which requires a classical signal, that you discover the correlations. The entanglement does not allow faster than light communication. It allows something subtler and stranger. Correlations between distant measurements that cannot be explained by any local mechanism, by any pre-existing information carried by the particles, by any signal that passed between them. The particles are not sending signals to each other. They are not sharing hidden information. They are simply connected in a way that has no analog in classical physics. John Bell put it simply: quantum mechanics is non-local. The universe is non-local, and there is no way to restore local realism that is consistent with the experimental evidence. We are left with a profound question. If the universe is non-local, if distant particles can be instantly correlated without any signal connecting them, what does this tell us about the nature of space itself? There is a possibility that has been gaining traction in theoretical physics over the last 2 decades. What if entanglement is not a property added on top of space, a weird quantum effect operating within an independently existing spacetime? What if entanglement is the origin of space? This idea, sometimes called ER equals EPR, proposed by physicists Juan Maldacena and Leonard Susskind in 2013, suggests a deep connection between quantum entanglement
and the geometry of space-time itself. In general relativity, an Einstein-Rosen bridge, also called a wormhole, is a hypothetical tunnel through space-time connecting two distant regions.
Maldacena and Susskind proposed that two entangled particles, at the quantum scale, are connected by the quantum equivalent of a wormhole. That the non-local correlation between entangled particles is not a mysterious action at a distance, but a geometric connection through a dimension we cannot directly perceive. If this is correct, entanglement is not weird physics happening inside space. It is the quantum substrate from which space itself is woven. The three-dimensional space we experience, the distances between objects, the geometry of the universe, would emerge from the pattern of quantum entanglements between fundamental degrees of freedom. Space is not the stage on which quantum mechanics plays out. Space is what quantum entanglement looks like at large scales. This remains speculative. It has not been experimentally confirmed, but it is being taken seriously by some of the most rigorous theoretical physicists in the world. And if it is true, it changes the question we should be asking about entanglement. The question is no longer, why do distant particles communicate instantly? The question is, why do we perceive distance at all? What if quantum entanglement is not just a quirk of particles, but a fundamental feature of the architecture of the universe? What if it is a clue that reality itself is structured in a way that makes our three-dimensional experience an approximation of something else entirely? Because the next chapter connects entanglement to the deepest question in modern physics. Consider what entanglement looks like from the perspective of information. Two particles become entangled. Their combined quantum state is described by a single wave function, one mathematical object that applies to the pair as a whole, not to each particle individually. This wave function contains information about the correlations between the two particles, information that is encoded not in either particle alone, but in the relationship between them. When you measure one particle, you gain information about the whole system. The information you gain about the second particle is instantaneous, not because a signal traveled, but because the information was never localized in either particle separately. It was stored in the entanglement itself. This is, in a precise technical sense, a non-local encoding of information. The information about the system's state is not distributed across space the way we would intuitively expect. It is stored in correlations, in a compressed relational form. In computer science, this kind of thing has a name: data compression. When a computer stores information efficiently, it stores the information in a compressed, correlated form, where the data about the whole system is encoded in the relationships between parts, not in the parts themselves. Quantum entanglement looks like a natural, fundamental implementation of exactly this kind of optimization. The universe, at its most fundamental level, stores information in correlations, in entanglement, rather than in separate, locally independent degrees of freedom. This is computationally efficient. It allows the universe to encode more information than a purely local, classical system of the same size would be able to. Is this a coincidence? Or is it telling us something about the architecture of reality? In 1993, physicist Gerard 't Hooft proposed something remarkable. And the following year, Leonard Susskind developed it into a more precise form. The proposal is called the holographic principle. It states that the maximum amount of information that can be contained within any region of space is not proportional to the volume of that region, as you might intuitively expect, but to the surface area of the boundary surrounding that region. This is deeply counterintuitive.
A three-dimensional volume of space contains more points than its two-dimensional boundary. You would expect a larger volume to be able to hold more information. But the holographic principle says no. The information is bounded by the area.
The most dramatic illustration is black holes. Jacob Bekenstein showed in the early 1970s that the entropy of a black hole, its information content, is proportional to the area of its event horizon, not its volume. A black hole packs the maximum possible information into the minimum possible volume, and that maximum is set by the surface area. The holographic principle generalizes this. It suggests that for any region of space, the physics inside that region can be completely described by information on its boundary. The three-dimensional interior is encoded in the two-dimensional surface.
In 1997, Juan Maldacena gave this a concrete mathematical realization. He showed that a specific theory of quantum gravity in a particular curved spacetime is exactly equivalent, prediction for prediction, to a different theory living on the boundary of that space, a quantum field theory with no gravity at all.
The two theories are different. One lives in 5 dimensions, includes gravity, and describes strings and black holes. The other lives in 4 dimensions, has no gravity, and describes quantum fields. And yet they are dual descriptions of the same physics. Every calculation in one theory has a precise corresponding calculation in the other. 2 different languages describing the same reality. The profound implication is that the gravitational, spatial, 3-dimensional description of physics is not the fundamental description.
The fundamental description lives on the boundary. The interior, the volume, the space, the gravity, emerges from the boundary theory, the way a holographic image emerges from a flat film. The interior is real. It has consistent physics, it makes accurate predictions, but it is derived. It is a projection of a more fundamental reality that does not itself exist in 3-dimensional space. We are living, potentially, inside a hologram.
Not in the science fiction sense, but in the sense that the 3-dimensional spacetime we navigate may be the emergent, large-scale description of a more fundamental theory that lives in fewer dimensions. The depth of the world, the very fact that space extends in 3 directions, may be an emergent property, not a fundamental one.
Now we can bring entanglement back into focus. If the holographic principle is correct, if the 3-dimensional interior of spacetime is encoded in a lower dimensional boundary theory, then quantum entanglement plays a central role in this encoding. Physicists studying ADS/CFT have found that the geometric structure of spacetime in the interior, specifically the distances between points, is directly related to the pattern of quantum entanglement in the boundary theory. Points in the interior that are close together correspond to regions of the boundary theory that are strongly entangled. Points that are far apart correspond to regions that are weakly entangled. Distance in space emerges from entanglement on the boundary.
The geometry of the world, the spatial relationships that define our experience of reality, is built from quantum correlations. Entanglement is not a property that exists within space. Space is the geometric manifestation of entanglement. This connects to the simulation hypothesis in a precise and unexpected way.
If you were designing a universe, if you were writing the code for a physical reality, the most efficient way to encode 3-dimensional spatial geometry would be to store it as a pattern of entanglement in a lower dimensional system. You would not need to explicitly represent every point in 3-dimensional space. You would need to store the correlations, the entanglement pattern, in a boundary theory. The 3-dimensional geometry would emerge automatically.
This is not what Nick Bostrom's simulation hypothesis suggests, that we are running inside a conventional computer simulation. It is something structurally deeper and stranger.
It suggests that the computational description of reality may not be a metaphor, that the universe may literally store and process information in the way that is most efficient, through entanglement, through holographic encoding, through a structure that resembles optimized computation, not because someone designed it that way, but because that is what the mathematics of quantum gravity requires.
The universe is not necessarily running on a computer, but it may be organized in the way that a perfect computer would be organized, because that organization is, in some deep sense, the most mathematically consistent way for a physical reality to exist.
John Wheeler, who coined the term black hole, spent the last decades of his career developing a principle he called it from bit. The idea? Every physical entity, every particle, every field, every structure derives its existence from answers to binary questions, from information. The universe is not made of matter or energy at the most fundamental level. It is made of information.
If this is correct, then quantum entanglement is not a quirky feature of particles. It is a foundational feature of how the universe encodes and stores reality. Entanglement is the universe's memory, distributed, non-local, holographically organized, and irreducible to any classical description. The observation problem we began with, does the room exist when no one is looking, becomes in this framework a question about information rather than about objects.
When no one is observing the room, its quantum state is a superposition, all its possible configurations equally real in some sense, none of them definite. The room exists as information, as a set of possibilities encoded in the quantum wave function of every particle it contains. The act of observation does not discover a pre-existing reality. It actualizes one branch of the wave function. It converts possibility into a specific configuration of information. Reality, on this view, is not a collection of objects. It is a running computation, a continuous actualization of information, in which the act of observation plays a constitutive role.
We began with a question that sounded simple. Does the room exist when no one is looking? And we have arrived at an answer that is, in some ways, more unsettling than a simple no. The room exists as a superposition, as a probability wave, as encoded information in the quantum state of its constituent particles. It is real, but it is not definite. It does not have one specific configuration that is simply waiting to be observed. It has many possible configurations, all of them real in the mathematical description, and the act of observation selects one. This is not nothing. It is not non-existence, but it is not the solid, definite, observer-independent reality we started with. Quantum entanglement tells us that this quantum reality is not organized locally. The information about the state of a system is stored in the relationships between particles, in correlations, in entanglement. And the holographic principle suggests that the three-dimensional space we navigate is itself encoded in a lower-dimensional boundary, that the depth and distance and geometry of reality emerge from a pattern of entanglement in a theory that is, in some sense, more fundamental. If this is correct, and the mathematical evidence for it grows stronger every year, then what we are is not what we thought we were. We are not solid objects moving through a fixed space. We are patterns of information, configurations of entanglement, in a quantum system whose full description lives in fewer dimensions than we experience. We are the code, experiencing itself. One response to this is nihilism. If reality is an illusion, if space is emergent, if the definite world is a product of measurement, then perhaps nothing matters. But this response mistakes the map for the territory. The emergent reality
The three-dimensional world of objects and distances and experiences is real. It is consistent. It has regular laws that we can discover and use. The fact that it emerges from a more fundamental quantum description does not make it less real. Temperature is real, even though it emerges from the motion of molecules. Consciousness is real, even if it emerges from the firing of neurons.
What the quantum picture changes is not the reality of our experience, but our understanding of its architecture. We live in an emergent reality, built from quantum correlations. Our bodies are made of atoms, whose electrons are described by wave functions. Our thoughts are encoded in patterns of neural activity that are ultimately quantum mechanical processes. The light that reaches our eyes has traveled across the universe, its quantum state entangled with everything it has interacted with along the way. We are not outside the quantum world looking in. We are inside it. We are part of the wave function of the universe.
And here is the thought that, once encountered, is difficult to release. If the universe encodes its information holographically, if our three-dimensional experience emerges from a two-dimensional description on a cosmic boundary, then in some sense, we are not exactly where we think we are. We experience ourselves as three-dimensional beings in three-dimensional space.
But the fundamental description of what we are may be encoded on a surface that is in some sense elsewhere. We are the projection, not the film. This is not science fiction. This is not metaphor. It is the most serious and mathematically grounded frontier of modern theoretical physics. And it leaves us with a question that physics as yet cannot answer. If we are patterns of information, if we are the code, does the code know what it is? We do. That might be the most extraordinary thing in the observable universe. Not that the universe encodes information holographically, not that entangled particles are correlated across cosmic distances, not that the geometry of space emerges from quantum correlations on a boundary, but that some of that information, some small, improbable fraction of the quantum state of the universe, has organized itself in such a way that it can ask questions about itself. We are the part of the universe that is looking.
And the looking, as quantum mechanics tells us, changes what is there. What we discover about the nature of reality is not separate from us. We are inside it. And what we choose to look at, what we choose to measure, to understand, to care about, participates in the ongoing actualization of which branch of the wave function becomes real. The room does not simply exist or not exist while you are not looking. It waits. And you, by looking, bring one version of it into being. That is not a diminishment of reality. It is the most intimate possible relationship with it.